All right. So I apologize. It's not going to be as nice slides as Britain or Matt. But what I wanted to talk about is derived quantities. So far we've been hearing, well, first define what actually derived quantities are. Why do we need them? Why do we need YT to actually compute them on your behalf? And the last point I forgot to remove because I'm not gonna cover that. So the concept on which it's building is the fields that Britton just talked about. So field is essentially just a way of thinking about some data that is either on the disk or that you can derive from that. One example, first of all, gas density, and that data container, which are ways of selecting and grabbing these fields from your hard drive or deriving it from it. And so again, like one way to think about it, I'm just like riveting what Britton just said, is that data container give you are really like the thing that are reading. Like you should never like filter your data manually because YT can do it for you. There's actually a good reason for that. So okay, as we said before, the first thing we do is load YT. In my case, here I'm just loading a sample dataset that's a Ramsys dataset. I'm a Ramsys person, so but it should work with whatever dataset you have. In which case you can just replace that load sample with YT.load and then the path to whatever you're trying to achieve. Here I'm just grabbing all of the data, which as Britton said, one should never do. But I just do it to get the maximum value. So that's argmax, that just tells us where the maximum of the gas density is. One could also have done what that was find max on DS, which would essentially achieve the same thing. Again, like that thing is typically an operation you don't want to do in a real case situation because that requires reading the entirety of the dataset to find a largest gas density and then just to return one number. If you have, I don't know, if you're doing galaxy simulation and you know the position of a galaxy, then use that position. If you do something else and you know you have a point of interest, just do it. But in my case, I don't know because it's just some data set that I downloaded. So I'm getting the center and then I'm creating a sphere around that center. In this case, like 100 kpc could be 10 meters if you're doing things on Earth, or below meters if you're doing things below Earth. Okay. And so what that does is, as mentioned before, again, I'm just repeating, it loads the data set and then creates some inputs, which is what's happened there. And we get slightly different logs just because, well, Ramsys is being verbally just a proteins. Okay, so what's the derived quantities? Now we have a data set, we have some container or some data container, in my case SP or even AT, so either all data or sphere. And sometimes, let's imagine you're, I don't know, working with a galaxy and you want to know how much mass is there in my galaxy. Or in this case, like how much mass do I have in my simulation? One way to do it would be what I just described here. So you take your data, you extract the cell mass, which you can get with gas cell mass. You extract the mass that's stored in particles, which we could get. And then you compute the sum of the two. And then I just display the results. And it works. So you're quite happy with that. But there's at least two problems. The first one, if I look at the memory usage of mcell and mbart, here I'm currently using 1 megabyte. I tried that on some actual dataset that I'm using for simulations. That number was on the order of tens to hundreds of gigabytes, just because I have a lot of cells. Which means that there's no way to run it on your computer, and also usually, well, it doesn't really make your cluster very happy when you're loading hundreds of gigabytes. And all of that to actually just return one single float number, which is the sum of everything. So in theory, there's no need to store any of this information in the RAM at all. Just like read it, sum it, and then discard it. And that's what derived quantities are for. The other issue is that now let's imagine that I move on in my script. I compute the mass in, for example, in the sphere. So again, like I get a different number. One thing that I hate when I script is that I have like two versions of MPart. One pertains to the sphere, one pertains to the entire data set, and I'm always a bit confused. And YT provides way of being a bit more explicit and like writing actually what you want to do in YT syntax instead of managing all the variables manually. Okay, and so if you wanted to clear things, you could also like write your own function that computed total mass and so on and so forth. Again, like I'm just reinventing the wheel over and over again. It would achieve the same goal, but then you have to re-implement everything. Good thing is I should have put it in. Let me do this. Yeah, the good thing is that usually YT has your back. And the way YT has your back here is through these quantities. And so essentially when you have a container, most of the containers, I think all of the containers probably, have dot quantities attributes. And that dot quantities has then some properties, for example, the total mass. And so if I do AD the quantities of total mass, I get these two numbers. First one being the total mass in the that's just the total mass, sorry. And you can compare that to the value that was up there, and well, not really a surprise, but essentially you're getting the same number. And the reason I'm using some m dots is because you have both the mass in the gas and the mass in the particles, so actually you get a tuple, you don't single value. And very similarly, you can do the same with the sphere, and well, again, unsurprisingly, you get the same number. What I like about that is that I don't have intermediate variables that are just stored in my local, so it actually makes it clear. And also, if you give that script to a student, or if you're a student and you give that script to your supervisor, well, they read it and they're like, okay, SP is a sphere, and then I'm computing quantity on that sphere, and I want the total mass. So by the syntax, it's actually self-descriptive. So that's nice. And you have a bunch of things that are present. You can compute weighted averages. So the way weighted averages works is that you have some fields. So in this case, for example, gas temperature, number density, or the x. And then you want to compute the average of these quantities with some weighting. And so for example, here I'm weighting by 1, so essentially no weighting. And that will evaluate that formula here. So, well, I mean, you know what a weighted average is. And so if I compute it, well, I get some, well, just ignore the log, that just because Ramses is a bit, again, like Ramses is a bit clunky. But then I get the average mass, I get the average density, and I get the average cell size, essentially. You can also do like mass weighting, exactly the same thing. You replace the ones by just cell mass, and you will get, well, the mass weighted or the volume weighted one. Okay. So that's nice. But I just want to like take a small detour to actually highlight what's actually happening under the hoods. And that's going to give even more reasons to try to use quantities whenever you can. Essentially here, I'm trying to argue that YT's way of doing it is better than the manual way of doing it, and probably the naive approach. Okay, so here I'm just going to illustrate what happens when I try to compute quantities on the sphere. So I'm just redoing it because just to clear some data so that there's nothing cached. And what I'm going to show is this is just because I want YT to spit out some information about what it's actually doing. And I'm also adding YT.mylog is a way of adding information in the logs. So I'm showing when it's actually reading the temperature, reading the mass. And so here what I'm doing is everything manually. So I extract the temperature, I extract the cell mass, and then I compute the average of the temperature weighted by cell using NumPy, so everything manually. And then you will see what actually is happening there. Okay, so what's happening is that I'm asking to read the temperature, and so far I have not computed which files should actually be queried, because Ramses is split in multiple files. In this data set, there's 16 different files. It needs to know which one it needs to read from. In this case, it's files that like file 8 to 11 needs to be read. Then it reads the density and pressure, because Ramses doesn't store temperature, it stores density and pressure, and using the ratio, you can actually derive the temperature. So you read it for all of the 4 files. I know you've asked to read the cell mass, so it goes again into the file, and now reads the density multiplied by the volume, and you get the cell mass. And then once you've done that, you can compute the weighted average, and you get, well, 1×10⁵ Kelvin. Okay. But you may notice that actually, if you count the number of, I'll just scroll down a little bit. If you count the number of times you've read files, you've actually read 4 files, and each of them you've read them twice. Because first time, the only thing you read was density and pressure, and then you discard these quantities, you just derive the temperature out of that. But then you need the cell mass again, and so you have to reread the file again. So now let's imagine that it's not a small data set, but you have thousands of files, and they weigh hundreds of gigabytes. That means that everything is going to be doubled. And also, if you were to do not only mass-weighted average of the temperature, but some other fields, then you would repeat that process over and over again. And it's tedious. I mean, it's not tedious, it's just super slow. Whereas if you use the weighted average provided by yours truly, what's happening now is that, so again, you're computing that you need to read 4 files, but now YT knows what it's gonna have to read because it knows you're asking for a weighted average. So you need the gas temperature and you need the cell mass. And so given that, it only reads what it needs once and then computes everything that's derived from that. And so it does everything in one single pass. So that's a major improvement if you are handling large data sets. And also at no point in time do you actually need to store the full temperature or the full cell mass in order to be able to compute these averages. All right. So essentially you get a speed up and also you get a smaller memory footprint. Also, YT ships with slightly more complicated and also quite useful quantities. For example, weighted standard deviations, which is just like the next moment when you have a distribution, which again you can write manually, but why would you? And again, like I mean, unsurprisingly, you get essentially what you're asking for. The weighted standard deviation returns both the, I forgot in which direction it is. It's actually documented. It returns both the average and the standard deviation. Forgot exactly. First element is the weighted standard deviation, and the second element is the weighted mean. So essentially, you get both in one single computation. And again, you can weight it by, in this case, cell mass, cell volume, or whatnot, whatever you want, actually. Okay, and there's a bunch more things. You can compute extra, so essentially the minimum and the maximum of some fields or some fields. You can compute where these extra are, so the maximum, the location of this maximum. And you can also do it with there's a typo here. There you go. You can also, as Britton mentioned, you can also evaluate a field at the location of the maximum of another field. So let's imagine you want the gas temperature and the cell size at the location where the density is maximal. You can do AD the quantity sample at max field values, or FP the quantities to do it in the sphere. You can also like compute some total quantity, so essentially just the sum of all of the fields you're passing. So if I do this, I will get the total mass and the total volume. And then some other things that are useful, center of mass, so it's just the center of mass, so it's like 10 times x, it's the mass weighted average of the positions. The bulk velocity, which is the mass weighted average of the velocities, as well as the angular momentum vector, which is, well, weighted, m r cross v, average over your gas and your particles, and you can control which ones are actually included there. Okay, so I have one more things to show, but so just to summarize what I mentioned, I don't know how because I don't.
Great. That's 7 minutes.
Oh, okay. Well, I think I'm gonna be shorter than 20 minutes, but
that's fine.
Yeah.
I was over.
So one reason to use derived quantities is because it's convenient. I mean, if you have a derived quantity that fits your purpose, then essentially by all means just use it. You don't have to write the same code over and over again. It's already been done. As I mentioned, it's more efficient because you're only reading your data once. And also, as I'm going to show, it's also parallelizable. You can parallelize it. And I actually have another script called Derived Quantities parallel. Is in the same folder. There you go. So here what I'm doing is I'm running with a data set that's called outputs 239, which is one of the one that I provided that you might have downloaded. It's like a few tens of gigabytes. And what I did is I created two ways of computing the average and the weighted standard deviation, either manual, so that's what I showed before, or using YT's built-in weighted standard deviation. And what I did then is, well, if you run it on your computer, you can either decide to run it manually by just doing Python Derived Quantities parallel manual, and then it will just do it manually, or you can do it using YTs. And I run that on one cluster I had access to. You can actually run it with MPI because YT knows about MPI. And then I'll describe briefly what's happening under the hood. But if I do it manually, it takes 2 minutes. And also the peak memory usage is 22 gigabytes on that data set. If I run it with YT, just on single one core, then the peak memory is 2 gigabytes, so it's a factor of 10 better. And that simulation is a decent simulation from a couple of years ago. It's like a factor of 10 to 100 smaller than what I typically use. So then total memory usage would be hundreds of gigabytes, which most computers can't hold. And then if you use multiple cores, for example, two, sorry, this is the timing and this is the peak resource usage. Then the resource usage goes down. And as you increase the number of cores, you're actually bringing your resources down. Actually, what's happening here is that YT, and we'll probably cover that later, has a way through the index that Matt talked about to cut the simulation into different pieces that can be processed in parallel. And so when you run it with MPI, it actually dispatches these chunks, it's called, to different MPI processes, and each of them does the reading. And then in the case of weighted average, you can actually, everybody computes their, for example, their mass times position, and then you just sum over all the MPI processes to get, for example, the bulk, the center of mass. And so these things can very well be parallelized. And so the way to do it with YT is actually you don't have to do anything. You don't need to think about MPI. The only thing you need to think about is to, well, tell YT that you want to use parallelism, and it will use it as much as it can. Whereas if you wanted to parallelize that, then you would need to think about MPI for pi and then split your simulation into chunks manually, and that would be super complicated. Whereas, well, this one, well, it's already been done. And with that, I think I'm gonna stop. There's, I think I covered pretty much all of the derived quantities that I could find, except for the spin vector, but it was very specific to.
Because they're attributes like that, you can always do dir. Right?
Yeah.
Dir AD, data container dot quantities and see what is there.
Yeah,
or they'll tab complete.
Yeah.
Or
so if you're here, you have angular momentum, bulk velocity, center of mass, which I talked about, external, which I talked about, maximum location, sample at max min, main parameter, which is some, it's useful in galaxy formation, which is why I didn't cover it, total mass, total quantity. So total mass is just an alias for total quantity, but where you call it from the total mass, and then weighted averages and standard deviations.
Thank you, Corentin. Great. Well, thank you for that lovely presentation and for getting us back on time after I so brazenly ignored timing. So we have lunch now. Should be just outside the room. If you haven't specified any dietary restrictions, try to use the least restricted things out there to save them for the people that have.